All right. Let's look at this problem. Again, we're looking for shear force and bending moment as a function of x for this particular problem. First thing you should notice is that the load is continuous across the whole structure. So that means we can get away with writing just one set of equations. The previous problem we just worked, we had to write a multiple set. So I'm going to cut it right here where it suggests at x, and I'm now going to try to decide what my strategy is going to be. Do I look at the left side free body or the right side? Well, in terms of reactions, both left and right, I'm going to need some kind of reaction calculation. So that's even. The size or the shape of the loading on the left side is trapezoidal. What's it on the right side? Trapezoidal. So that seems like about the same. The advantage of the left is that this segment would be in terms of x. What would the stuff on the right be in terms of? Yeah, it would be 18 minus x. And you can see that that would just be kind of a little more tedious to deal with. So I think it's going to be easier to use the left side for this problem. And since I'm going to the left side, I want to find my reactions at A. So let's do that first. I'll draw a free body diagram of the beam. And we will assume that we have a positive shear force at A and a positive shear force at B. And then I want to replace this distributed load with a concentrated equivalent at a location. Now, I do know the area of a trapezoid, I could find that, but I don't usually remember the centroid of a trapezoid off my head. If you look in the front cover of your book, you will find formulas for that. I think it's going to be a little easier for us to break this up into a rectangular piece and I'll do a different color just so you can maybe see it, and then a triangular piece. So the rectangular piece is going to act right in the middle. And I know it's 18, so I know that'll be 9 feet from A. And what's going to be the value of this rectangular portion? Yeah, it's going to be, the base is 18 times the height of 1, so it's just going to be 18 kips. Now the triangular part, again, you probably know the area of a triangle, 1/2 base times height. So 1/2 base, that's 18. What's this height here? The thing not to be tricked about is to see that 3 and think it's 3. It's not. That's the total height here, 3. But remember, we've just subtracted off the rectangle, which is 1. So this height is 2. So it's going to be 1/2 18 times 2, which, interestingly enough, is also 18. And I remember the centroid of a triangle as 1/3 the distance from the big end. So 1/3 of 18 is 6, so that would be 6 feet from here. And it would be, so if you add all that up, what am I missing? 3, right? So the distance between these would be 3 feet, if you need that value. But all I'm looking for is the shear at A. So to get that, I'm just going to sum my moments at B and make sure that's in equilibrium. So there's my equilibrium statement. So let's do that. Starting at B, both these forces are going to create what kind of moment about B with right-hand rule, sign convention? Positive, right? And interesting enough, they're both 18 kips, so I'll write this in shorthand. The first one has a moment arm of 6 feet. The second one has a moment arm of 9 feet. So that takes care of the moment for the two applied or concentrated equivalent forces. What's the moment about the shear at A? Is that going to create positive or negative moment? Negative. So I'll have negative. The shear at A and the distance is 18.
Cam, I have a question.
Yeah.
Is there a reason why you assume positive shear?
Just did. We're going to end up writing an equation for shear, right? So I want to know what the starting shear value is. So what is that? Looks like the 18s cancel and you just get what? 15. Is that good? Somebody check that for me real quick.
Yeah.
I think that's good. Okay, so let's write our equations. So I'm going to come over here. I'll try to draw this a little bigger so you can see it easier. So we're going to cut this at some distance x. I know I've got my shear force acting up here of 15. And I'm going to have a rectangular portion and a triangular portion in my loads. And we'll come back to those in a second. And then, of course, at the cut, I'm going to have positive shear force and positive bending moment. So let's start with the rectangular portion. I know that concentrated equivalent force is going to act through its centroid. I'll call that F1. And what is F1 going to be? So what is this area here? Well, it's a rectangle. So we know it's base times height. So the base is x. And what's the height here? I forgot to write that on there. 1 kip per foot. So that's easy. It's just going to be x, right? And what's the distance? D1 from the cut to F1? It's half the distance, and the distance is x. So D1 is going to be x over 2. Any questions about that? Now we got to figure out this force F2, which will be the triangular part, right? So it's going to be 1/2 the base x times the height. Oh, we've got to find the height. How are we going to find the height? So what is the value of the load at any position x? I'll call it W. Well, if you look at it, it's a linear line, right? And a linear line is AX plus B. So what is B? B is the value of the load when x is equal to 0, right? What is the value of the load when x is equal to 0? 1. So I know B is going to be 1. A is going to be the slope, right? What's A going to be equal to? What's going to be the rise over the run? So what's the rise? It goes from 1 to 3, so that's a rise of 2 over a run of 18. And so that's a slope of 1/9. So it looks like my load W is going to be x over 9 plus 1. Now it's easy to check. If I plug in x equal to 0, what should I get? 1. So I plug in x equal to 0, what do I get? 1. What's the value over here at x equal 18? It should be 3. So I plug in x equal 18. 18 divided by 9 is 2, plus 1 is 3. It works. So I know this is the value here. But what is the actual value of the height of the triangular portion? What will be the total height minus 1. So what is this minus 1? X over 9. So I now know that my force 2 is a triangle 1/2 base times height. If you do a little work there, that just becomes x squared over 18. And the distance D2 the distance from this cut to the centroid. What's a triangle? So it's 1/3 of the distance from the big end, and 1/3 of x is x over 3. So now that we got all that geometry done, we can now compute the moment. So let's go back now and sum the moment at the cut, and let's make sure it's in equilibrium. So when I do that, using right-hand rule, what kind of moment is this, positive or negative? Positive. The moment about the cut due to F1 and F2, are those positive or negative? Right-hand rule. They are positive. So the first one will be F1, which is x, times D1, which is x over 2. The second one will be positive, and that's going to be F2, which is x squared over 18, times D2, which is x over 3. And then get all the way over here, I got this 15. What kind of moment is that going to create, positive or negative? Negative. 15, and what's the distance? X. I think we got everything, right? So let's solve for the moment. So the moment as a function of x is going to be, I'll put everything on the other side of the equation. I'll rewrite them. So this looks like it's going to be x cubed over 54, and that will be negative. So x cubed over 54. This is going to be negative x squared over 2. And move that to the other side. It's going to be positive 15x. And that should be the moment with units of kip feet. Do I know the moment anywhere in this structure? What's the moment at a pin? 0. So let's check. Is x equals 0? Does my equation give me a 0 moment? Well, let's see. Plugging x equals 0. That term goes away. That term goes away. That works. Where else is the moment 0? At this pin. So we should also check that the moment at x equal 18 is 0. Now that one I can't do off the top of my head. You guys will have to help me out with that. So somebody have to plug in 18 through that cubic equation and let me know that it's 0. Now while somebody's doing that, I'll go ahead and now we'll sum forces in the y direction to find the shear. So there's my equilibrium statement for that. We're assuming forces up are positive, so what kind of force is this shear force? It's negative. F1 and F2 are what? Positive or negative? Negative. So F1 is x. F2 is x squared over 18. And then I've got this 15 kip reaction, which is up, so that'll be positive. So when I solve for shear, this is what I get. Looks like I get negative x squared over 18 minus x plus 15. And that should have the units of kips. Anybody verify that this was true on the moment?
Yes.
Yep. Okay, great. Now what do we know about the shear? Do we know the shear force anywhere? Yeah, we solved for it. So we know that the shear at x equals 0 should be 15. And that's an easy one. Put in x equals 0, you get 15. Now we didn't solve for the shear at B. We could have. We'd have found the shear at B to be what? I think it's negative 21, just looking at the equilibrium of this thing. And if you plug in x equal 18 here, I hope you'll get negative 21. That one you don't have access to. But we do have the notion that the derivative of the moment should be equal to the shear. And if you take the derivative of this equation, you do get that. So it looks like we're in pretty good shape. Any questions about that one? I just wanted you to see that sometimes the descriptions can get a little complicated. So you can imagine this same idea, but if we were to work the right-hand side, all these variables here, all these x values that you see would have been what? 18 minus x. So it would have been a little more tedious, a little more cumbersome to work those, but you could have.
I have a question.
Yeah.
Where did the x over 9 come from on the x?
That's the slope of the loading curve.
Oh, okay.
Right? Rise over run. So I went from 1 to 3, so that's a up of 2. And then I went over 18, so 2 over 18. But then it's reduced to 1 over 9. Okay.